Good morning, ladies and gentlemen. I am Andres Rueda. I'm the project coordinator for this task. This is Alejandro Salaro. He's our lead designer, and besides him is Carlio Persona. He's our lead programmer. So, as part of this project, Overhead Crane Automation Kit, we came about it by teaming up with a local company called AAR. What they do is they overhaul the landing gear of aircraft, and as part of that complex process, they do electroplating. Now the electroplating process, for those of you that are not familiar with it, consists of dipping a part in a chemical solution and passing a current through it, so that the elements in the solution stick and form a layer around the part. This is due for maintenance and rust prevention. In addition to that, the issue that they have in particular is that the electroplating process can take anywhere from 4 to 14 hours. That is a shifting time, that is a variable time. And the problem that they have is if they leave a part if they dip a part that's due to be removed in the so-called third shift, anywhere from 10 p.m. to 6 a.m., so let's say 2 a.m., they have this issue of either having to pay a worker overtime, 4 hours, or they have to just simply leave the part there until it's due to be removed early in the morning, and it has an extra thick layer of whatever element. Chromium is extremely tough, and since it's extremely tough, it's extremely time-consuming and thus expensive to machine properly to dimensions. So that extra thick layer is, like a full day of machining just to get it down to dimensions. So it's very, very critical to get it down at the right time. Now, so they have this problem of, the part not being able to remove it at the proper time. So how could we solve it? After some thinking, we decided that the best solution is to just automate the crane. What we plan to do is to add a couple sensors, add a timer, add some microprocessors, so that we are able to tell the part, hey, it's 2 a.m., this part is due to be removed at 2 a.m., it's 2 a.m., please shut off the current, and lift up the part. And that way and move to the unloading area. That way the part is, ready for the next step, and we have saved the company a lot of time and hence money. Some things that we have to take into account with this solution is that this part needs to be retrofittable. This kit needs to be retrofittable to their already existing cranes. They're not looking to, completely renovate their electroplating process. They simply want an easy, business-friendly solution, something that will actually work. It has to be easy to use. We're working there. The operators is not going to be an engineer; it's going to be a blue-collar worker with somewhat limited experience in automation. We don't know how computer literate he is necessarily, so we have to keep that very much in mind. That it has to be very user-friendly, and it has to be affordable and serviceable as anything in the industry. Now I'm going to pass it off to our lead designer, Alejandro Salaro, and he's going to lead you on to the review.
Thank you, Andres. So, as part of some of the sensors and some of the design considerations that we have, one of which is an important factor, which will be a sway control for the future. So the reason this is important is because, one, it saves a lot of time. The operator doesn't have to stop and go, constantly try to get the part in control so as to not hit anything. And two, it's safe for that. If the operator is moving the crane, moving the part, he's gonna have to keep that in mind, that he might actually hit something if he goes too fast, too slow, or so on. So in terms of our sway control sensors, what we're gonna do is we're gonna create a fuzzy logic program that it's gonna measure the angle of attack. It's going to measure, first of all, it's going to measure the distance that it has to travel. Then in between that distance, it's going to measure the angle of attack that it initially takes. And then it's going to apply that angle of attack towards the second half of the motion, the trajectory, in terms of deceleration. So, and then some of the other things that we had are, we have to keep in mind that we have to turn off the electricity to the current before taking out the part. If for some reason the electricity is not turned off before the part is being taken out, an arc could actually jump from the bath to the part, causing hundreds of thousands, depending on how much the landing gears cost, but considerable amount of money in damages. So what we came up with was a timer style of device that will attach to the electrical box, and that once that timer is up, it will cut the electricity and then proceed on to taking the part out of the bath and into the loading area. In terms of the crane, and to actually find out its position, we have two different types of designs that we're considering. We have a mechanical design. We have one with mechanical design, mechanical sensors, and we have another one with a wireless sensor, which Carly will later on explain. The mechanical sensors will be more of putting magnetic sensors all along the rail of the I-beam, and that will feed into the sensor that's on the crane, and that will tell the program exactly in what position the crane is at. And in terms of the vertical positioning of the actual part, we're gonna do a sensor with a retractable line that's gonna attach onto the crane hook. We're gonna program that crane hook to know the certain distance between the bath and the part, and then the actual operator will measure the distance from the bath. The distance apart will actually go into the bath. You will input that distance into the computer, and then the crane will know how far deep to insert the part. And now on to standards and considerations, so Carly will present.
In terms of design, there are three main constraints that you have to account for. Number one is the actual model, the ER18, in which AR actually uses in the actual chromium plating process. This is the main crane that they use for that specific area, and it's the one that we have to account for when we're actually doing the model. In terms of actually control, rather crane communication, we're thinking of two design methods. One is the actual manual splicing of the control, then by using the wires and actually hooking up our control kit into that way. Another one is actually using a wireless system that utilizes a wireless controller that AR already has installed in one of those cranes. So we're just going to try and supplant that control module using our own attachable kit. In terms of sensor location, we're thinking about using a manual and a wireless system. The wireless system mostly consists of multiple sensors at different locations to actually give feedback to the microcontroller and provide actual positioning of not only the actual trolley of the crane, but actually the hook and the vertical distance in that method. In terms of standards, we're going to use Occupational Safety and Health Administration, which is a government-funded agency. For that specific standard, we're going to focus more on a permanently installed overhead crane that is not used for construction. We're also going to consider the ASME standards. In terms of global awareness, we do realize that cranes are not only used in the U.S., but also in multiple parts of the world. Also used by people with varied backgrounds, not only college graduates or even people with masters, but also just standard blue-collar workers that might possibly have graduated from high school, but in some other parts of the world, they're not as lucky to actually work, to actually go to school without actually graduating. In terms of that, we're just going to make it as safety-proof as possible, also account for any errors that are operating errors. In terms of feasibility of the crane kit, we're also going to make it more accessible in different parts of the world. We're also going to make it, as I said, as safety-oriented as possible to make it easier to understand and utilize. We're also going to focus on the sway control. And that's it for the presentation.
Does the crane exist, or is this crane gonna be a brand-new design as part of your proposal?
The crane's already installed,
Okay,
so the crane's already existing, this is what we're retrofitting to already existing crane. Yeah, you can kind of see them already installed there.
So this is an actual picture of the factory that we're gonna be working in. These are the bats, they're all aligned, and you can see the cranes up here in the audio.
so all structural design issues, statics and dynamic issues and all of that are already fully addressed, and the performance of the crane has proven that those designs are satisfactory. So you're not in the structural domain at all, you're just in some kind of controlling and timing mechanism design.
Correct.
That's all you're doing?
Correct.
Okay. All right. So that pretty much mutes all of my questions with those answers. All right.
Yes, sir.
Hey guys, you had mentioned the fuzzy logic actually. Why fuzzy logic, and do you consider any other control algorithms for this?
It's just one of the main controls that we're thinking of right now. We do have other considerations.
In terms of actually, fuzzy logic is not only the method that we're actually considering, because we read from basic literature that there are other methods besides the fuzzy control which utilize the actual microcontrollers and actual sensors to actually give a positioning in real time and actually function based on those inputs and actually to actually control and maneuver the crane. So,
Do you have a plan for testing this?
then we still have to talk to AAR to be able to utilize their crane, because right now because we missed their maintenance time by 1 day. So we need to make sure to actually get in touch with them to see if we can actually get an additional crane they're not using at the moment to actually do our testing.
I have a question. As far as measuring the raising and lowering the landing gear, have you thought about how you're going to monitor the cable going down? What kind of thoughts have you
Yes,
put into
there
that?
has been a.
Right. So we're gonna have a rotary sensor, which and then we're gonna attach that to a retractable line
Okay.
type of thing. The line is gonna be attached to the hook, so the program's gonna have an idea of where it is in terms of distance. Now, in terms of lowering the part, what we'll do is the actual operator, they'll measure the distance from here to the hook. And then once they measure that distance, they can put that distance in the computer, and then the computer will know the distance from here to the hook is the distance that it needs to go down, up to that distance.
Because when you started talking about it, I used to work as a mechanic, and back in the old days, we used to have carburetors, and you just start going into fuel-injected systems, and they still use the distributor, but they use a big, with a Hall effect sensor, and it had many multiple points, so it would tell what position that rotor was related to the engine. So I thought of maybe something like that, so you can measure what revolution it is.
Okay.
But then it's going to do many revolutions as it's slowing, so you have to keep track how many revolutions
Right.
you're really at. You know,
Right.
but just a thought.
We'll take that into consideration. Thank you.
What is your sensor, again, to tell how high it is off of your fluid level?
The fluid level?
Yeah, how do you detect that?
We don't really have a sensor for the fluid level. That's
Well, for the part outside of the fluid level, the delta.
This is the part where the worker will actually input that. Like the fluid level, it's one of those variable considerations, just like that part height, because this is the landing gears vary very much by aircraft type. So they do all types of landing gears. So it's very variable process. So we can, as much as we wish that we would be able to automate the entire, from step A to step Z, due to the variableness, and we find that it's just simply better for not only the not only for them in terms of monetary value, but also in terms of our project scope. Do you simply leave some user input, some, some human element to it? Because otherwise, we might end up running into unforeseeable errors that, this landing gears, they cost anywhere up to like $500,000. So it's something that it's one of those things that's just really better to have some.
So user inputs will probably address your concerns, and I think their system is ready for those user inputs to customize the input to the conditions, the gear size, fluid level, and all of the timing and all of those other inputs.
Right, the actual operator will have to manually measure the distance from here to the hook, which is where our sensor is going to be
That's what I was-
positioned at. And then once they actually measure that, they're going to input that into the program, and then that's when the computer, it'll know how far to go down.
Okay.
Just a question, because you're integrating into a pre-existing process already, it's always very important to understand all the detailed aspects of that process. So, for example, with his concern, if the process already calls for a manual dipping, per se, you might be able to trace back to the starting point and use that instead of needing a user measurement and a user input. So just be aware of considering other options that still minimize impact to the pre-existing process.
Right.
Now, there's something, as another added feature, when they're actually trying to electroplating process, they have to inspect the part first and then figure out which section of the part actually needs to be undergo the electroplating process. So most of the time, it's not the entire part that actually goes in, so it's only a specific section, maybe a square inch of it actually needs to undergo the process. So in order to facilitate that and reduce the machining time and whatnot, they actually tape sections of it around the actual section that needs to be plated. And from there, they actually dip it into the part based on orientation. Like for this part, is the part that actually needs the section that needs to be electroplated is already in the part. So if it was somewhere like here, these parts would already be
Masked.
masked.
Right.
And just the orientation would be completely different than what you see here. So it's also based on orientation, not just a specific part that you can just measure.
Absolutely. But like I said, that's what I'm saying. So just be aware of that and try to incorporate that as much as possible.
Okay, thank you very much.
All right.
Okay.
Thank you, guys.